All right, welcome to our March edition of our afternoon on group theory. It is my great pleasure to introduce the first speaker of the afternoon, Emmanuel Breuillard, coming from Oxford University.
Well, thanks a lot for the invitation. Great to be back in the US. So, so the title is Random Character Varieties, and it goes both with Oren Becker and Peter Varieties. So, the talk will be about random groups. So I guess you're all familiar with this notion. So I'll start with some basic information about them. So we start with a finitely presented group, K generated, R related. Okay. And we're going to fix K. So for the talk, we're going to fix K and R. But the relators are going to be chosen in a ball of radius n, L, little l, and the length, so the radius of the ball is going to go to, I'm going to choose them at random in a ball of radius L, either by using the uniform measure or using the random walk measure. But the important point is that they are all independent, and the length will grow. Okay.
So your R doesn't depend on L. Your R.
So my R for most of the talk will not depend on L.
So not like in the usual model that you have many relators.
Yes.
For you have just
I'm getting I'm getting there. So in the usual model, which it's called Gromov's density model, the little r is allowed to vary with L. And typically what people take is that they take, so you have at most 2k minus 1 to the L words in the ball of radius L, okay, into a constant. So they take the d parallel, where d is between 0 and 1, and they call this the density. And this is called, for d is fixed, it's called the Gromov model at density. Okay. And then you study the properties of such a random group. But for my talk, we'll consider what's called the few relators model, where R is fixed. Okay, so it's fixed R. So it's here. What do you mean?
So R is fixed and L is fixed over.
No, so
they are the same.
It's fixed for me, but you should think of K and R as fixed, and maybe K equals 2, R equals 1.
But all relations have the same length.
And all relations have more or less the same length, roughly L. So you can either think that they are all in the same, on the sphere of radius L, or in the ball of radius L, or you could take the random walk on the free group. So then the length can vary, but roughly. But for most of what I'm going to tell, I mean, it's a good idea to start with K equals 2 and R equals 1. So what do we know? So in the density model, that has been studied a lot. What do we know? So we know, for instance, that if you take very few relators, so if you take less than, if the density is less than 1 over 12, so I was saying just before, if you are in the pure relator model, the density is 0, of course, right? At the bottom, okay? So the pure relator model is sort of included in the density model, that d equals 0. So if d is small, less than 1/12, then the group has small simplification 2 prime 1 6. So we know a lot about such groups. This is very easy to prove, just from the definition of small simplification. On the other hand, when d is less than 1/2, it's a theorem of Gromov and Olivier that it's infinite and hyperbolic. So when I say that, I mean, not every single group like that has the property, but most of them. And most of them here means all except maybe an exponentially small proportion when L goes to infinity. Okay. So so actually Jan Olivier was in one of those offices for this. So And when D is between 1/3 and 1/2, then we know that the group has property T. And we also, and we also know these two things. So if D is positive, then it's a theorem of Damani, Krasitsky, and Girardet that it has property Fa. So the group does not split. And so every action on the tree has a fixed point. Yeah, and there is some more recent work by Kozma and Lubotsky that establishes that as soon as the density is positive, then there are no non-trivial n-dimensional linear representations. So if you fix n, then the probability that you're going to have some non-trivial, so with non-trivial m image, sometimes it's Z mod 2 ZZ, because that's some parity issue, not one or Z mod 2Z, then for most of these groups, there will be no non-trivial n-dimensional linear representation for fixed n. On the other hand, we have to be careful here because there's a big difference when you fix the dimension of the linear representation or if you let it vary with the group. Because it's a theorem of Danny Wise that C prime 1/6 groups, they are actually, they are cubable, they act on at zero cube complex. And we know by recent work of Hegel and Wise that such groups actually are linear, they embed in Hags. So in fact, they embed in sub GL and Z where n is huge, okay, depending, of course, on the presentation. So we know they are reasonably finite, okay, but nevertheless, if you fix a dimension, Kozma and Lubotsky show that there are almost no representations. Okay. So
meaning the dimension will really depend on each particular in your random model, because you said they're linear, but
yeah,
but
they're all linear, but somehow if you pick one at random, the dimension of yeah. So yeah, on the other hand, in a few related models, so if you take, let's say, fewer relators than generators, and of course you map onto Z most of the time because you have fewer relators than generators. So you map onto Z to the K mod something that's less small dimension. So you map onto that. So you have non-trivial representation. Okay. So in the Kozma-Lubotsky theorem, it's crucial that D is bigger than 0. It's crucial that the density is positive. Okay. For property Fa, it's also important that D is positive, although I have a conjecture of where the threshold should lie. But okay, so on the other hand, if you take any R and K and you take a finite group, any finite group, then the probability that your random group maps onto the finite group is not as L tend to infinity, because you have only a finite number of relators that you need to satisfy. So you have a random walk on the finite group, and you need what's the probability that the random walk hits the identity in this finite group. That's a positive probability, independent of L. So you're going to have lots of, a positive proportion, non-vanishing probability that you map onto a given finite group. And then any finite group has many linear irreducible representations. So that's another way to construct irreducible representations of random groups. So, but they will have finite image. But more generally, if you don't take a finite group, but you can take any virtually solvable subgroup of G and C, okay? And then again, this is Kesten's criterion. So Kesten's criterion is a criterion for meanability, which is true for every group. Every finitely generated group is amenable if and only if the random walk, the probability that the random walk goes back to the simple random walk on the K graph goes back to the identity does not decay exponentially fast. So it's at least x with the minus little over. Okay, so that's Kesman's criterion. So if you start with such a group, such an amenable group in GL and C, then you will see that the probability that your random group with R, let's say a fixed number of relators, will map onto this thing will be sub-exponentially small, at least sub-exponentially small. It doesn't decay exponentially fast. It may not be positive proportion, but at least it doesn't decay exponentially fast. So this again gives you lots of representations, linear representations with non-trivial limit, okay, in fixed dimensions. So this really shows that in this Cosma-Lubotsky result, you cannot, you have to take at least many relators, and the number of relators you need to take is at least has to grow with L.
I ask a question about B. Why is this like, so basically what you're saying that given a finite group, the probability is not vanishing, that it is a quotient of inferior model.
Inferior, yes.
Is it like, who proves this? Or
No,
just-
it's obvious because so if you have a finite group, the probability that a random walk hits the identity, now after a while it becomes equidistributed. So the probability that you hit the identity is like one over
Okay,
the
so
side
one
of the
divided by the size
side
of
of the.
right?
So, and you have it R times because you have R elements.
But then it is one divided by something to the R,
With it R.
but then it's zero.
No, it's 6, R is 6,
It's fixed, the number, all numbers.
because I'm in the few related model.
They fix really. Very related.
Yeah, I fix the number related. So it's 1 over G to the R. So it's a
Okay,
fixed
yeah.
number. Okay. So it's non-dimensional. Of course, if you take more, if R goes to infinity, you're there, then it's more. Okay, so so the first theorem is a kind of a extension of the Cosma-Lubotsky theorem to the case of the few related models. So when you have a fixed number of relators. So there it shows essentially the same conclusion, but you can allow representations, linear representations with virtually solvable image. So it shows that even though it may not be a linear representation may not have finite, so it may not have trivial image like in Cosma-Lubotsky, it must have virtually solvable image. Okay. So there is a caveat. So here there's an assumption. We use the Riemann hypothesis. Right? So I'll come back to that. But,
I'm confused. Didn't the result tell you already that you don't have?
yes.
I don't have.
Yeah, so the result is they allow if you allow the number of relators to grow, then you can actually prove that you cannot even get a virtually solvable image.
So this is the density model.
That's in the density model. Okay, but in the few relator model, it's not true, and this was what I told you in the previous slide. Okay, it's not true. You can have non-trivial image. However, even if it's not true, you cannot have like large images. It has to be virtually solvable. Okay. But of course for this you need at least k. You need, so that's crucial here in purple. You need at least the number of relators has to be at least the number of k.
Can you have infinite image? So you say virtually solvable.
Yes, you can. You can have infinite image. So that's the previous slide. So you can have infinite image because you start with arbitrary with your favorite, let's say, 2 generated virtually solvable subgroup, and then you map onto it by your random group, and then the probability that that this will be a subjective mapping does not decay exponentially fast. Okay. So, okay. So I just remind you that I don't know if it's necessary with this audience, but just remind you that virtually solvable means that there is a finite index subgroup which is solvable, and the T's alternative says that if you're a linear group, so a subgroup of GLN, a finite generic subgroup of GLN, then the following are equivalent. Being amenable is the same thing as being virtually solvable, and same thing as having no non-abelian free subgroup. Because there's no need to define amenability, because otherwise you don't know what's a amenable group in this seminar, you won't be able to log in. Okay, so I said assume GRF, so this is kind of weird, right? So the proof relies on the Riemann hypothesis, but I'll tell you exactly what we need about it. The Riemann hypothesis is a statement that the zeros of the zeta function are aligned on the critical line. So we need it not just for the zeta function of Q. In fact, we don't care about Q so much. We care about number fields and arbitrary number fields, and we need the kind of zeta function of an arbitrary number field to be to have zeros on the real line, on the critical line. So we don't. So sometimes GRH includes L functions. We don't deal with L functions. Just the delegate zeta function is important to us, and we don't need the full strength of it. What we need is that there is a kind of a zero-free region around 1. And that's the zero-free region we need. It depends on the discriminant of the number field, but unfortunately, it's not. It's a bit stronger than what is currently known. Okay, so I want to mention that the formal consequence of the theorem of the first one is the following kind of uniform non-immutability. If you fix the dimension, you fix the number of generators. Sorry, the missing hypothesis here. If you take every x1, xn, xk in GLN, and you suppose that they do not generate a virtually solvable group, so you suppose it's non-amenable. Forgot this assumption. Sorry. Non-amenable, then the probability that the random walk goes back to the identity decays exponentially fast. This is Kasten, but this says that the exponential decay is uniform and does not depend on the generated decay. Uniform here. So it doesn't matter the matrix we take two matrices, as soon as you generate non-immutable, the probability that you come back to the density decays exponentially fast with a constant that does not depend on anything, depend on n, on the GLN. That's it. So why is that a formal consequence? Well, the reason is that if not, then you would come back to the identity with sub-exponential probability, but then this would mean that you would have a non-trivial image of your random group with non-virtually solvable image. Okay, so it will contradict the previous theorem. Okay. So this is kind of a formal consequence of the previous theorem. However, I already knew about this because it also follows from the uniform Tits alternative, which is here, which says that you can in the Tits alternative you find a free subgroup, but the uniform version tells you that you can actually find the generators of the free subgroup in the ball of bounded radius indicated graph of the company. And knowing this is easily implies the return probability, uniform return probability statement. Okay, so this theorem here does not need GRH, okay, because this does not need GRH. This requires some number theory though, but not the Riemann hypothesis. On the other hand, the previous theorem is in a way stronger than this one because this one is just a formal consequence. Okay. So now I'm going to tell you a bit more about the proof of the first theorem, and in fact, a stronger statement, which relates to character varieties. So the way we prove that there are no non-virtually solvable linear representations is a bit like in the T alternative. The idea is to say, okay, suppose you had a non-virtually solvable image, then you take the Zariski closure, and then you divide by the solvable radical, and then you would have a map into a semi-simple algebraic group with Zariski dense image. Okay. So you would have a representation of your random group with Zariski dense image in a semi-simple algebraic group like SLNC. And so that's called such a representation, the space of such representation of your group into a semi-simple group is called the representation variety, because the moduli space of such representations is a variety. It's an algebraic variety, right? Its form of gamma WG it's a closed algebraic subvariety of G to the K, which is defined by the equations given by the relator, W1, WR. So these are words, but the words they define algebraic subvariety of G to the K. So the moduli space of representations, gamma W to G, is an algebraic variety. Okay, it's an algebraic set. It's given by polynomial equations. Okay, so that's called the representation variety. What's called the character variety is almost the same thing, but up to conjugation. So you identify two representations if they can be globally conjugated to one to the other. And it's usually denoted like this with a double bar, which means the GIT quotient, because it's not just literally the quotient, it's only on an open set. It's actually put to the equivalence classes. But the reason it's written like this is because it's actually a variety, an affine variety. And one way to define it properly is to say that it is the variety whose coordinate ring is the ring of polynomials on the representation variety that are invariant on the G, the conjugation action. So that's a nice variety. And it parameterizes the representations of gamma W into G up to conjugation. Okay, so I'm only going to be interested in not in the full character variety, but in what I call the Zariski dense part of the character variety, which is an open set in it, Zariski open set, so almost all of it. But it's the points. So remember, points correspond to representations. So it's the points whose corresponding representation has Zariski dense image in G. Okay. And it's a fact that those points in G to the K, whose subgroup that generate is Zariski dense, it turns out it's a fact that it's an open, it's a Zariski open set. So it's actually well known that it contains a Zariski dense, an open set, but it's actually open. It's a Zariski open set. Okay. So the set of pairs in SN2, for example, the generate Zariski dense subgroup, that's an open set.
Could be empty.
No, it's always
You're on.
as soon as K is bigger than 2. So every semi-simple Lie group is generated by 2 elements.
Sorry. Yeah, but the intersection with X, R and X
Yeah,
W, you have relation.
that's right. You're right. The character variety itself can be empty. And the Zariski dense part can be empty. But omega is not empty. Okay. But
I think I was saying omega
Kind of.
XW can be.
yes. Okay. There may not be any interesting implementations. Okay. Okay. So So what are the interesting questions we can ask about geometry varieties? Well, first thing, maybe we'd like to understand the dimension. How many irreducible components this variety has. Also, everything is defined with Z because your algebraic, your Lie group can be defined as Z. So
Is it obvious that it's a finite number of irreducible components? That there is an
yeah, so every algebraic variety has finite number of irreducible components because as an algebraic variety over C.
Okay, yeah.
So, so it's finite number, and the Galois group acts on them. So you want to understand if it's transitive or how does it act? Some people are interested in singularities. So all of this has been studied a lot in the case when the group is a surface group. Okay, but my group is not a surface group; it's random groups. It's quite different. You can ask, are they faithful representations in there? Are they discrete representations? Okay. So next few slides, I'm going to just give you some examples and just skip of them because otherwise I won't have time to talk about the rest. But so for example, if you start with a higher rank lattice like SLNZ, so this has nothing to do with random groups, but this notion of character variety depends only on is well defined for every presented group. So if you take a higher rank lattice, then it's known that by superrigidity that the Zariski dense part of the character variety is finite, essentially the superrigidity theorem. And in this case, for SLNZ, it's just 1 point. And when it's Q irreducible and the Galois group acts Q reducibly, then people say that it's a Galois rigid representation. So an example of a Galois rigid representation is this one, the Bianchi group as PSL2, then bracket omega. It was proven by Whiteson and some recent work on profinite rigidity by Whiteson and others that Galois rigid. Okay, another example is the surface group, as I was saying. The surface group, we know the dimension of the representation right by early work of Rapinchuk, Chernosov, and Benyas-Kivitz. And for the way they handle SLN, and Liebeck and Shalev handle the general case by a different method. And so this is the answer. We also know that it's absolutely reducible in this case. As Nicolas was saying, you have to be careful because sometimes the representation of the variety can be empty. So, for example, if you have a Bohm-Slack solitar group, then it's not too difficult to show that you cannot have a linear representation with Zariski density.
It's not true for any solvable.
What?
It's not true for any solvable.
This is the non-solvable one.
Ah, okay, sorry.
Yeah. So another playground is the case when G goes SL2C. When G is SL2C, you can really play around because when you have just two generators, one relator, and SL2C, you can do a lot of just playing around because there is something as the Frege-Klein coordinates, which parameterize the representations, the two generated subgroups of SL2C. So if you know the trace of A, the trace of B, and the trace of AB, A and B are your two generators, then you know the group AB up to conjugation. The group generated by A and B up to conjugation in SL2C. And furthermore, if you give me three different complex numbers, then I can find two matrices A and B with those traces. So the character variety of the free group, the two generators in SL2C is the affine is A3, C3. Okay, and what's more, the trace of a word W in A and B can be written down as a polynomial in X, Y, and Z. The trace. And so these polynomials are really fun to play with. They are very hard to say anything interesting about them because there's no, you can just generate them. but there's no understanding, global understanding what they are. But nevertheless, when you try to understand the representation variety of the random group related to W with W as relator, then you have to study this polynomial. So so by the way, how to prove this? This is very simple, right? If you have a word, let's say A squared, B, A inverse, B cube, etc., then you know you have Hamilton K there, tells you that you have this. K Hamilton tells you this, where X is the place of A. So you can always replace A squared in such a word by something of smaller degree. So you can reduce the degrees, and at the end you just have a linear combination of A, B, and AB. But that's why you have this. Anyway, so in this case, I said it's kind of a playground because you can understand exactly the locus of pairs that generate a Zariski-dense subgroup for SL2C. And this is this exact open set here. It's G2 minus a closed subvariety, which is the subvariety of pairs that generate a non-irreducible subgroup of SL2C, and 3 lines corresponding to dihedral representations, and a finite set of points corresponding to the irreducible finite subgroups of ASU2. Get to this finite list. Okay. So, when you list this down, you can actually play with the computer. You can put this in a computer algebra system, and you can ask the computer algebra system to compute for you the dimension of the representation block. Okay. So I did this. I played a bit with this. In fact, there is a saved routine by Ashley, Breuillard, and Lawton available to compute these polynomials, and then you can ask what's the dimension. So
there are already ready tools to compute it, or you just program?
Yeah, so actually they have a paper where they give a routine, but I had to optimize. I use them, but I had to optimize it.
Just curious, and what kind of tool you use?
Sage, I would say using Python. But this was just to play, just to get an understanding of with the random groups. Anyway, with random groups, you cannot go very far because of exponential explosion. So you can only go to, you can sample. The length of the word cannot be very long. Yeah, so maybe I'll keep this time running out, but I just wanted to say one thing. So I have very little idea of how to prove that these representations are faithful. So I suspect they are really not faithful, but representations of random groups. But I know almost nothing, and the only trick I have up my sleeves is to prove that they are not faithful is the Varieties of Magnus, which tells you that if you have one related group, they are isomorphic if and only if the two relators are conjugate to the inverse. And so if you take a random group, then it has this property that the trace, so the trace of W is equal in SL2, is equal to the trace of W twiddle, where W twiddle is the same word, but read from right to left, so the reciprocal. And that's really special because of SL2. But it implies that whenever you have W as a relation, you also have W twiddle as a relation. So unless your word is palindromic, or conjugate to its palindrome, then the corresponding representation is not faithful. Okay, so the one related group cannot embed message. But in general, I really don't know, and so I think that's an interesting open problem related to also model theory of groups, is to determine if you are given a word, maybe some W, and you know that W of A, B is equal to 1 and some two matrices A and B. Can you deduce that also V of AB is equal to 1, where V is another word? Can you find the words V that this relation implies? So can you, WAB equals 1 implies, of course, that W squared AB equals 1, and that any word in the normal subgroup generated by W in the free group will vanish also at A and B.
So it's some sort of a radical, right?
Yeah, right. So, but maybe many more words are like that. And so this is what people call the universal theory of SL2. So if you're given finitely many words, can you describe all the other words that the vanishing of these finitely many words imply?
So do you know example of W's for which there are more V's than in three groups?
Yeah.
Okay, this.
Okay. But yeah.
And for SL3, is it easier or?
No.
But so what, sorry, what was your context?
No, I know it's not a conjecture, it's a question. So can you describe all the words that must vanish? If I give you a word, and I tell you this word vanishes on A, B, SLP. So I give you a word, and I want you to tell me all the words that have this property. Whenever this word vanishes, these are the words vanish.
So that is radical, right? All the
Radical.
polynomials which are killed by zeros,
Yes,
double.
that's right. Yeah. It's like computing in algebraic geometry, it's like computing the radical of the variety. So you're given generators of an ideal, and you want to compute the radical of the ideal, or the full ideal. But here it's in terms of combinatorial, it's in terms of words on three. Okay, so here's the main theorem. So this describes the character variety of an arbitrary random group with few relators. So G here is a fixed semi-simple algebraic group. If you want, you can take a set C or SLNC. And you take a random group with with K generators R relators. So there are three cases. If R is bigger than K, so there are at least as many relators as there are, then typically the character variety is empty. Okay, so there would be no direct cadential representation. They all be non-direct. So okay, and the probability of exception. So there may be exceptions, but the exceptions are exponentially small probability. And so the interesting case is when the number of relators is one less than the number of generators, for example, 2 and 1. So in this case, it's interesting because the character variety is not empty usually, but we can show it's finite. And on top of that, the Galois action is irreducible. So Galois moves around the points, and it's transitive. So it's the most interesting case also because it identifies this finite. So you have this finite variety. So it's a finite set of points in, let's say, SL2 cross SL2. These points will be algebraic, will have algebraic entries because it's finite sets. And they produce Zariski dense, so this generate Zariski dense subgroups and rigid subgroups, right? So you cannot deform. Okay, so they are finitely generated subgroups of G, which are rigid, you cannot deform them, the augmentation variety is finite. And they are Zariski dense. So, and this gives a wealth of interesting Zariski dense subgroups. of given antibiotic.
So, sorry, I'm confused. The difference with theorem one. So in theorem one, I thought you said that.
So theorem one,
Or
yeah, theorem one is a consequence of point one. So I was assuming R bigger than K.
okay, theorem one will have bigger than K,
Yeah.
so the direct Stevens part is in
Right.
fact the IC closure has to be.
Has to be equal.
Yeah.
Yeah. Okay. So again, we have to use DRH, so it's slightly less, it's epsilon 0, depending on the K. Here one, let's say consequence one. And in two here, we can further show we have an estimate on the number of points of this finite character variety. It's at most polynomial in L, and it's at least, that's the hard part, at least L over the log N. So we have a lower bound on how many points you get, how many different Zariski-Lenz representations. So, okay, so now I have maybe 3 minutes to tell you about the proof. That's a bit short. So, I'll tell you a couple of things. So maybe I'll summarize. I'll just say that the proof is based on number theory, but the main idea is to reduce modular primes. So you reduce mod phi, and then you reduce to a counting problem where you have to count the number of points of your variety mod p. So if you count the number of points of your variety mod p, then you can access the dimension of the variety. Right? Because the Lang-based estimate tells you that the number of points in the variety mod p is basically p to the power of the dimension. So that's the rough idea. But now you have to choose the primes, and you have to average over the primes. To average of the primes, you need a version of Cherepov's theorem, and this is an effective version also because the character variety here that we look at, they are defined over a field whose degree grows with the length of the word. So it's not a fixed degree. It's not fixed. Yeah, the degree is huge. So everything that's known in number theory is usually called fixed degree, and there are some estimates. But for us, it's absolutely crucial to know the estimate and how it depends on the degree. That's where DRH comes in. So, in order to compute the number of points, we use kind of a Fubini argument where we average over the primes on the one hand, and we average over the random walk, we average over the words on the other hand. So if you fix a word and you average over the primes, this will tell you some information on the dimension of the variety. But if you fix the prime and you average over the words, then you can count the number of points in your character variety mod p. And in order to count this, what's really behind it is the uniform mixing of the random walk. So you have your group V of p, but p will be quite large. In fact, p would be like e to the CL. The prime will be of this size, and you have your random walk in this group V of p, and you need to show that it distributes really fast. So for this, you need what's called uniform mixing or uniform exponential mixing, and that's related to the notion of expanded graphs. And so that's the estimate you need to show that the probability of a random walk in G of P to come back to the density is like 1 over the size of the group up to a small error. And this is exactly what being an expander tells you. So for the proof to work, you need to know an estimate on this probability. But you see, you sum over the generating sets. Because what is this thing? It's the number of elements in the character variety mod p So it's basically the number of solutions of the equations W1 equals 1, WR equals 1 in G of P to the K. So you have these algebraic equations, you need to count how many solutions you have. So that's exactly the number of solutions, that's exactly this thing here, when you sum over the W's, or sum over the X's. Okay. So you need to know that the K graphs of G of P with respect to an arbitrary generating set is an expander, and is a uniform expander independently of the generating set. So there is a conjecture in this setting, which is the following: that if you fix the number of generators and you bound the rank of a finite simple group of B type, then the family of all K graphs with K generators of finite simple groups of B type of bounded rank has to be a family of expanders. In other words, there should be a uniform spectral gap. So we don't know this importantly, but we know approximations to this. We know this holds for almost all generating sets. And this proof of that uses approximate groups. But unfortunately, for this application, it's not enough to know it for almost all. We really need it for all, because even one bad generator will ruin completely this count. So we need it for all. And so this is the last term. We prove that that it's true for all generating sets. We have uniform estimates. But we cannot quite prove the conjecture, we cannot quite prove it, but we prove it for almost all primes.
The conjecture is for all primes or
The conjecture is for all primes, even out of
for
primes.
all but finite number
No, so finite number doesn't really matter because it would be a finite set.
Yes.
But we prove that except for density zero
Family of primes.
family of possible counterexamples of primes, and then it's true.
And density, you take density in all primes or what are you?
Density in primes, yes.
Does you count the number?
Count the number of primes
Primes to until some
value.
and divide by the number of primes and it goes to zero.
It goes to zero. Okay, so that's the last theorem. This clock is
It
on.
does not work.
Sorry about that.
No, you're fine.
You don't show us the page.
Are there any questions for the speaker? Let's start in the room.
Can you explain the rootings of your example?
The groups,
And you can give it on the slide.
before, so like
Yes.
this one, the Bluetooth Sapir example. Yeah, so that's an interesting group. It appears in a paper of Dalton and Sapir, and it's an example for reasonably finite nonlinear groups for which we can explicitly compute the character variety. It's made of 2 points. Sorry, I forgot one parenthesis here. So there are 2 points. They are permuted under Galois. And it was an interesting example for me because it answered the question of LNNO, because she wanted to know, because she wanted to know whether a finitely presented group can have rigid representations with non-integral forms. So here it's not integral because there is 1 over because she proved the theorem that for I1s of algebraic varieties that are rigid, then they have to be integral. So she was kind of worried that maybe her theorem is part of a very general, it was just a very general fact. It's not. So that shows it's not.
Could you show theorem one once more?
Yeah, So yeah, so a consequence of this theorem is in particular that if R is bigger than K, then almost all random groups have the property that when they act on hyperbolic space, they fix a point.
Is something more, or can you say something about the finite index subgroups of, like, if it is a random group, like in model? Let's say finite index subgroups. For
Yeah.
fixed index of.
For fixed index, yeah, I haven't put that. Yeah. For fixed index, that's a different question. So it's sort of, if you fix index, then I guess if you have some representation, you can induce to the bigger group.
Right.
So that
So
probably
it basically is the same.
same conclusions if you fix index.
So, compare the previous theorem stated that there is the probability of having actually an infinite solvable image is larger than some decaying exponential. But
Yes,
is it still decaying or is it
it's decaying as soon as it's yeah.
because of
as soon as it's infinite, yeah.
So in fact, the typical behavior is that it's only finite.
Typical behavior, yes, but the only time if R is bigger than K. And if R is less than K, you map onto Z. But if R is at this K, then
Right now, it's not immediate. That's the typical behavior is only finite. Otherwise,
what?
otherwise theorem one is
What do you mean? No, it's four.
that is for a fixed solvable group, you have exponential
You have
decaying probability, but
Yeah.
so
No, so
if there with infinite probability,
yeah, if you
some solvable representation.
I think if you're not concerned with this exponential, if you allow a larger set of exceptions, then I believe you can change virtually solvable by finite. If you just want something that maybe the probability of the exception just goes to 0, then I think you can pick.
By using your method?
By using the theorem. Once you know that it has to be virtually solvable, if you have virtually solvable group, then you're still now studying images of random groups onto a virtually solvable group. And if it's infinite, then typically it's not going to, the probability that it maps onto it can come wrong, unless it's really finite.
And conversely, could you?
Because it's just the probability that you return the data.
Could it be possible to have an interesting quantification of how the probability to have a really non-trivial character, right? For instance, probability that a random group subjects on a free group of rank 2. I guess it's going to be some exponential. But, I mean, it's going to be exponential, but.
Yeah, so when it subjects on
That's not, if they subject on a free group of rank 2, then they have a big factor, right?
they have big argument.
That's only virtue.
So
But that's only virtually, yes.
so these random groups, they do virtually subject.
They virtually subject on, yeah, as soon as I think it's a thing of pi or something that as soon as there is less than 2, the defect is at least 2, then it's large.
So
That's good.
it means that,
That's for every kind of example.
but it also means that the
Index.
the level, the index of the virtual group has to be very large.
That's
right?
right.
Right, perhaps we give the online participants a chance to ask questions. All right, so then let's go ahead and take a 3-minute break while we switch between speakers.